Hi, I'm Boshi Yuan. Let me present our paper, MDML, Superfast Privacy-Preserving Machine Learning for Malicious Security with a Dishonest Majority. This is a joint work with Shi-Feng, Yongxiang, Zhang, Ning, Dawu, and Shi-Feng. Okay, sorry. So, first some introduction. In the setting of multi-party computation, a set of distrustful parties want to compute a public function on their private inputs. So ideally, there would be a trusted third party that computes the result for them. But in reality, we don't have this trusted third party, so they have to rely on a cryptographic protocol called MPC, which ensures the privacy of the input and the correctness of the output. And also, when the function being computed is a machine learning model, then we call it privacy-preserving machine learning, or PPML for short. So as for the security model in MPC, we have passive protocols and active protocols. Also, we have honest majority protocols and dishonest majority protocols. So this work studies maliciously secure dishonest majority PPML, so hence the name MDML. So typically, PPML protocols consist of two parts. The first part is an underlying MPC protocol for basic arithmetic circuits. This is usually done by using existing protocols like SPIS, SPIS2K, etc. The second part are the protocols for ML-specific operations, including truncation, comparison, and vector dot product, etc. And this is where we make improvements. So let's look into the state-of-the-art in PPML in the security model that we concern. The first work by Damgård et al. Uses the SPIS2K protocol as the underlying MPC protocol, and this is the first protocol in this model. Hence, we refer to this work as SPIS2K+. There's another work by Damgård et al., which studies the evaluation of quantized neural network, but this is out of our scope. And also, their underlying protocol is the same as SPIS2K+. Hence, we mainly compare our work with the former one. So, our contributions mainly includes improving the efficiency and decreasing the online communication. We use circuit-dependent preprocessing technique with the SPIS2K protocol and introduce new truncation, comparison, vector dot product protocols in the context of circuit-dependent preprocessing. So we have achieved that the online communication of truncation plus multiplication is identical to that of multiplication, which means that truncation is free in the online phase. Also, the vector dot product protocols consumes only one element per party, regardless of vector length. We also implement our protocols and open source the code. Next, some preliminaries. We make use of the SPIS2K protocol. And the SPIS2K secret sharing is an additive sharing with authentication. I'm not going into the details with authentication. All we need to know is that addition can be done locally and multiplication can be done with a classical beaver triple. We also make use of existing circuit-dependent preprocessing technique. The core idea is that in the preprocessing phase, every wire in the circuit is associated with a shared value, lambda x. And in the online phase, the parties compute delta equals x plus lambda x, and then opens delta x in the clear. So for the input gate, the parties will choose a random shared value lambda x, and then mask x with lambda x and open the delta x. Since lambda x is random, the delta x can be opened securely without revealing the information of x. And also the addition can be done locally. For multiplication, it is a bit complicated. In addition to a multiplication triple, the parties need to prepare a random sharing lambda z and locally compute the small delta values. Then in the online phase, the parties compute the big delta z values as follows. So the correctness of these protocols can be easily verified by expanding the formula here, so I'm not going into the details. So with circuit-dependent preprocessing, the online communication of multiplication reduces from 2 elements per party to 1 element per party. So this is what we need with CDP. So based on CDP, let's propose our constructions. The core idea is that previous work used CDP to only improve multiplication, but in this work we show that CDP can also be used to improve ML-specific operations like vector dot product, truncation, and comparison. So first, for the length m vector dot product, a naive way is to do n invocations of multiplication. Of course, this is rather inefficient. So in the context of circuit-dependent preprocessing, or CDP, we can write out the representation of the delta z values and expand the formula like this. The key observation is that the summation term here can be computed locally. So only the term lambda z requires interaction between the parties. So this is our new vector dot product protocol. The parties in the online phase only need to compute the delta z, the share of the delta z locally, and then interact to open delta z in a clear. Hence, the online communication of vector dot product protocol is only 1 element per party, regardless of the length m. While in previous work, we have to invoke m times of multiplication protocol, resulting in 2 m elements per party. Next, for the truncation protocol, so the truncation means we truncate a shared value z prime to a z, where z equals z prime divided by 2 to the d. The traditional classical truncation protocol is as follows. The parties generate a truncation pair, r prime and r, and we model it as a functionality f trunk pair for convenience. Given the trunk pair, the parties will mask the value with r prime and then open it in the clear. Then do the truncation locally. Finally, they subtract the random mask from the value. Okay, how can we make it more efficient? So in the context of CDP, we observe that in CDP we already have delta z prime equals z prime plus lambda z prime. So this equation is in the same form as the c prime value here. So a natural question is that can lambda z prime be used as r prime? The answer is yes, since in multiplication we already have that the lambda z prime value is random, and hence the r prime value is also random. We can combine truncation with multiplication. We can integrate truncation into it. Hence, we no longer generate the lambda values as random shared values. We instead generate it from the trunk pair functionality. So this is our multiplication with truncation protocol. In the preprocessing phase, the parties generate the lambda values from the truncation pair functionality. And in the online phase, they open the delta z prime values in the clear and do the truncation locally. And hence, we require only 1 element in 1 round in the online communication, while in previous work, they have to do 1 round for multiplication and another round for truncation. As for the comparison protocol, for the sake of time, I'm not going into the details, so please refer to our paper for technical details. And finally, for the implementation, we implement the online phase in C++, and we benchmark the offline phase using the MP-SPIS framework. We focus on the 2-party setting in the evaluation. Although our protocol supports arbitrary n parties, we focus on 2-party setting. And we mainly compare our protocols with SPIS 2K+. So for the online phase, we implemented AlexNet inference on CIFAR-10, Tiny ImageNet, and ImageNet datasets, and we observed significant improvement in terms of time and communication. We also implemented ResNet 18 inference on CIFAR-10, and we can do inference in less than half a minute in the LAM framework, in the LAM network setting. As for the preprocessing phase, since we use circuit-dependent preprocessing, the preprocessing cost is slightly higher than previous work. And we can see that the factor is slightly less than 1, but compared to the significant improvement in the online phase, and concerning that the preprocessing phase is of constant round complexity, this decrease is acceptable. Finally, for the conclusion, we propose PPML protocols in malicious, secure, dishonest majority model. We propose new protocols from circuit-dependent preprocessing. We propose new truncation protocols, vector dot product protocols, and comparison protocols. We implement and benchmark our protocols and passed the artifact evaluation. And that's all. Thank you.